let's go ahead and begin. So everyone join me in welcoming Camilo Montoya. He's our PhD student from our department, advised by Dr. Gail Grantroff, and I think a couple other members of his committee are here as well. Um, so
Definitely, Mira.
yeah, Professor Yotov, namely. So yeah, he'll talk to us about prime number theory and the Riemann hypothesis. So Camilo, please take the floor.
Hey guys, hi. So, like I said, I chose to give a more general audience talk. Uh, I told them this would be a way more accessible, including more fun talk, because there's gonna be a lot of really cool visualizations. Gonna start some of the historical background, some old, some proofs you probably guys already know, like the infinitude of primes. It's gonna start really slow, but you'll see as we go on, the pace will eventually pick up. All right, so let's begin. Right, so prime numbers. So we're talking about just basics of prime numbers. Everybody knows the definition of a prime number. A prime number is a natural number with exactly two divisors, one and itself p. So for example, like as I have right here, you guys can see my mouse, right? 23 is prime, but 77 is not. Obviously, 77 is 7 times 11, which 7 and 11 themselves are primes, and so that I'm also taking it as like a definitions, in that slash theorem, the fundamental theorem of arithmetic. This fundamental theorem of arithmetic, the one that says that every natural number has one and only one up to permutations and stuff, one and only one prime factorization. That's called the fundamental theorem of arithmetic. Uh, I believe it has tons of proofs, but one of my favorites, one of the ones that I know is the one given in Professor. What is this? Disquisitiones Arithmetica. This is like the book. I think Gauss, Carolo Federico Gauss, whatever. This is the one that he wrote when he was like 19, bro. This guy proved one of the most important theorems when he was 19. It's amazing. Anyway, so these are what prime numbers are. And then, so this is the graphic that I was mentioning. So this is how this is the graphic, but I'll explain it before we get into it. So now, I hope you guys can see my mouse move. And if you can see my mouse, so this is a circle, and this circle has diameter 1. And right next to it, we have another circle of diameter 1, and so forth. All of these are all circles of diameter 1, all placed exactly next to each other. And then this is a circle of diameter 2. This is another circle of diameter 2, and so forth. Such that, for example, naturally, two circles of diameter 1 fit inside one circle of diameter 2, right? And so forth. This is going to continue because we're going to use, so like I said, for example, look at this top line. These are all circles of diameter 1, diameter 2, diameter 3, diameter 4, 5, 6, 7, 8, 9, and we can go down as far as we want. And then, but the whole point is, this is going to show how numbers naturally fit inside each other multiplicative. For example, 3 circles of diameter 3, if these are the circles of diameter 3, exactly 3 of them will fit inside one circle of diameter 9. Because naturally, 3 times 3, 3 times 3 is 9, or you can say, yeah, 3 goes into 9 3 times. So 3 circles of diameter 3 will go into one circle of diameter 1, and so forth. The same is for every number. And so now what are we going to do? We are going to kind of squish this whole picture down. We're going to put all these, we're going to overlay all these circles on a common axis. And it's going to create one of the most beautiful images you've ever seen in your life, which is rather unexpected. this is the first few. This is the beginning. So again, the small ones are all circles of radius 1. Then the next one that's a circle of radius 2, and exactly 2 circles of radius 1, diameter 1, and then fit inside the circle of diameter 2, and so forth. And this had, I forgot to what number this goes, but for example, the thing to note here is the thing to note here is that the is exactly where certain circles meet. For example, here, if you look, I can't zoom in. I don't think I can zoom in as a PowerPoint, but here at 2, here's 2. Look at this red vertical line. This means that here only 2 circles meet. Only the circle of radius of diameter 2, and then obviously 2 circles of diameter 1, because they'll fit in all the circles. Those, well, I mean, whether you call it 2 because you're only looking at half the side, or 4 if you want to look at both sides, that indicates where the prime numbers are. So for example, 3 also only 3 circles of diameter 1 fit inside 1 circle of diameter 3, because 3, and that's this red vertical line showing it, 3 is a prime number. But once you go to the next one, to 4, if you look at 4 and you zoom in, you're going to see that more than 2 circles touch at that point. Namely, for example, not only does the circle of radius 4 and the circle of radius 1, but also you have 2 circles of radius. I keep saying radius. You have 2 circles of diameter 2 touching also right there at 4, because 2 divides 4. Therefore, that's why there's no vertical red line here, and that signifies that 4 is not a prime. It has more divisors than just 1 and itself. So this picture naturally, out of this picture, naturally primes just emerge. They just pop out. So now what we're going to do is we're going to zoom out, and we're going to keep zooming out. You're going to see how this is going to get beautiful, and it's going to keep getting consecutively more beautiful. Bam, that's one more zoom out. And you can start seeing some of the intricacies. Again, vertical lines, wherever you see these vertical lines, that's a prime number. That's where it just so happened that only 2 circles are touching. Namely, 1 and the big circle of radius of diameter p, because these are exactly the prime number. And let's zoom out a little more to get some more. Bam! Look how cool that looks. So this is, and again, you see the vertical lines here are where the primes just happen to lie. This is exactly, here we overlaid all these circles, all the circles from here. When we put them all on a common axis, the natural picture that we got are these. And naturally, only in some places of certain circles of certain diameters, only 2 of them touched, and those are exactly the prime number. So now I think we're gonna just, this is from the beginning, starting from the left here is from the beginning. We're gonna just move out to like far down the number line, for example. Actually, no, this is kind of towards the beginning. So this is the beginning of the graph. I guess just colored red, but for example, here you see the first few primes. Here's 2, 3, 5, 53. Wherever you see 2 guys next to each other, you have a set of twin primes. So whenever you see these, so 59, 61, a set of twin primes. 101, 103, this is a set of twin primes. And so this is how it looks, again. And then, but this is just the beginning of the picture. Let's go way out into a number line because the pattern, and the intricacy continues, the beauty continues. So this is how it looks way out in the 9,000. For example, this guy right here have 9,733. This happens to be a prime number. If you follow it up till here, the only two circles touching are the circle, obviously one, and then the enormous circle of diameter 9,733. Then, so that signifies again that 9,733 is a prime number. Here, 9,739. Okay, no, I thought they were twin primes, but here's a set of twin primes in the 9,000. 9,767 and 9,769. This is a set of twin primes all the way out in the number line. You know what I mean? And we're still obviously relatively small, but so you see the intricacies, you get the idea of how. So yeah, and then this is just the sieve between 20,000 and 20,000 and 20,100 and 20,500. The intricacy continues, and the beauty just doesn't end. It just gets more and more beautiful. And then orbital ab chow or ab cow. This is order out of chaos because this is what we're seeking. We're trying to. This looks chaotic. This looks this looks virtually unpredictable. And so the goal of prime number theory is to find the order inside all of this chaos.
Okay, I have a question.
Yes, sir.
Can you go back in the slides? Back in your slides?
Yes. Which one?
A little bit more. Okay. So I can obviously see here specific lines, right? In your
the vertical lines?
These the slanted lines.
Slanted. Oh.
Well,
no, so the slanted lines, yeah, they're just created naturally because of we're starting with circles. Remember, we're starting from the left. We're starting with circles of increasing diameter. And so every time I add another circle of increasing diameter,
okay, I understand this. I understand this, but
there
are few such lines. They are not. I would have expected many more such lines to appear.
Oh well, it's because so it has also to do with computing power. As you see, like for example here, whatever the final circle that you can see here is a circle of who God knows what diameter that is, but it's really large. But the thing is, the whole point is they have to stop somewhere because of computing power. If not, if you had infinite computing power, you could do this for all natural numbers. And so here's because eventually you gotta to make these pictures. The guy I spoke to, he's from Paris or something. He gave me permission to use these images, and obviously he told me he made them on AutoCAD, the engineering software, and obviously it's up to however much computing power his computer has. How many of how far and how many of circles he could fit into one image. Alright, so back to our presentation here. So what is prime number theory? Again, the goal of prime number theory is to unlock the secrets of these primes, to find the order inside all of the chaos. So yeah, and this is where I like to make the comment that there's a lot of branches of mathematics where you could argue, where you could make the argument, and I'm convinced by it. I agree with it. You could make an argument. So where I'm talking about the philosophy of mathematics, and namely the question of invented versus discovered. there's a lot of branches of mathematics that you could make a very convincing case that it is invented, clearly. But this is one part of mathematics where I have yet to see what about this is quote unquote invented. This is like close to the God, what Hawking's quote, God created the integers, the rest is the work of man or whatever. So yeah, this is what I'm trying to say here is but to me, I have yet to see what about this is invented. This looks like just the natural way that numbers just happen to fit inside themselves. Nobody invented anything. Seems basically as natural as I could have, especially creating this image, for example, to creating this image to specifically show it, because this image will identify all the primes. I don't know what about this could even be considered as invented. To me, this is discovered. This is why number theory is one of my favorite branches of mathematics, because number theory to me is as close to actual magic and as close to the mathematics being that we're actually discovering things rather than just inventing. All right, so this is quick. I'm not going to take too much time here. Everybody knows this. This is Euclid's proof of the infinitude of primes. There's a lot more, there's a lot more proofs. Everybody knows this one. This is the classic one, about 2,300 years old or however, whenever he wrote his Elements. It's a statue of Euclid. And it's just proving that there's the primes, that if we continued that picture, we would never run out of these vertical lines that indicate where there's a prime. And the proof goes very simple. I'll just go over very, very quickly. If you, by contradiction, assume that there's a finite list of primes, P1 through PR, and you have a finite complete list of primes. If this is the case, then just consider the number capital P equal to the product of all of those guys plus 1. And then again, I took it by definition / theorem 0, the fundamental theorem of arithmetic. There needs to either, then this number capital P, this number capital P, either it is prime itself or it's divisible by primes. But by construction, by the way we constructed this, it cannot be divisible by any of P1 through PR. Therefore, this capital P, again, is either prime itself or it's divisible by a prime that is not here on your original list of P1 through PR. And QED. And QED, that proves it by contradiction that you can never create a complete finite list of all the primes. So we all knew this. There's an infinite amount of primes. So now, a way to find primes is this the sieve of Eratosthenes. It's a fast way the Greeks found to find all the primes up to a given number. For example, this little table is gonna find all the primes up to like 120, I believe. And so what you do is you're gonna write down all the numbers in order up to like whatever number you want, and then, for example, start with 2. You're gonna circle 2 or something, and then you're gonna cross out every other multiple of 2. In other words, all the even. And then go to the next one, 3. Circle 3 because 3 is gonna be prime, and then can't cross out every other multiple of 3. And then just continue this process until you'll have a complete list of, at least in that range, of all the prime numbers. So here's a little visual of exactly this in order. So look, so he's gonna start with 2, and now cancel out every factor of 2. 2's prime. 3's prime. take out all the remaining factors of 3. 5's prime, take out the factors of 5. 7's prime, 13's prime, and so forth. You get this, and you can go up to you don't have to go to 120. You can go up to, again, however much computing power you have. But this is called the sieve of Eratosthenes, and this was a way for the ancient Greeks to find prime numbers. A pretty efficient way, at least especially by their standards, pretty efficient. Okay, so now we go back to talking about primes, and we wish to find what I call the holy grail of prime number theory. The holy grail of prime number theory would be this function, p of n, or p sub n, whatever. It's the function that returns the nth prime. The first prime is 2. The second prime is 3. The third prime is 5, and so forth. So happens that the 100th prime is 541. And so that if we could find the analytic closed form whoever found, and it's probably impossible. I mean, especially after Gödel and his incompleteness theorems, chances are this function probably doesn't exist. At least not in closed form or in things like that. Or an analytic version or a closed form version.
Camilo, the function exists, of course, you just defined it, but
No, but I meant a nice formula for it. Of course, the function exists. I mean, in theory, the function exists. What I meant is the closed form analytic version.
Okay, I have a question.
I plug in 25,023, and it spits out 287,341.
This is exactly what the computers do. But why do you need why this idiosyncratic attitude? I mean, why do you need a closed formula for it?
Oh, because this would be the function. This would be the function of the prime. This would be the function that spits out all the primes. And as far as we know, getting this function, it's not even, to say it's hard is a severe understatement. This is like beyond hard. I mean, Euler tried using polynomials, and they have polynomials that spit out a lot of primes, x squared plus x plus 41, or things like that, but obviously it misses primes and things like that. I'm talking about the perfect expression that for every n spits out p of n, the nth prime. Now, this function, as far as we know, nobody's ever found it, and like I said, probably there is no closed form for this function. And this is what I would call the holy grail of prime number theory, because this would be as good as it gets. But like I mentioned, this seems near impossible. For this to exist, man, we'd have to get pretty lucky. So the next best thing is what Gauss and Euler and then Riemann after them did, which was, instead of trying to find an analytic expression for this function, don't worry. So these prime spirals, forget it. These are some really cool prime spirals, but I don't have time to talk about them. The next best thing was not the exact formula for the primes, but the prime counting function. So not the function that spits out the nth prime, but what we call pi of x, which is the function that spits out the number of primes less than or equal to some given number, x. And we call it by convention pi of x, or pi of n. And so since we couldn't get that p of n or p sub n from the last slide, the next best thing is this. And Gauss was already thinking about this. He already had this analog n thing eventually. And so this is called pi of n. So for example, for n equals 100, how many primes are less than or equal to 100? There's exactly 25 primes. You can count them. You could actually go back to here, and if you counted them here, you'd see that the last prime is 97. They're exactly, and 97 is exactly the last prime before 100. So, but whatever. And so that, take the quotient, the ratio, there's 25 primes out of the first 100 numbers. So about 25% of them are prime. And now increase it. Then 1,000. About 168 of them are prime. I mean, exactly 168 of them are prime. So roughly 16.8% of those, of the numbers up to 1,000 are prime. And so the table continues. This is the number of primes up to, here we have 1,000,000. Here we have 1,000,000,000 and one. Oh. Yeah. This is 1,000. This is a billion, and so forth. But anyways, you get it. This is the next best thing.
What is the 18?
The prime counting function. And so this is what Riemann's. This is kind of very ugly. I should have got a better graphic. It ends up being a step function because it increases by 1 every time it hits a prime. So, like for example, pi of 7 is or pi of 10 is 4 because there's only 4 primes. 2, 3, 5, and 7 are primes less than or equal to 10. But if you do pi of 11, it just jumps. It's a step function. It jumps to 5 because 11 is a prime number. So this function, if you graph on the x-axis n and the y-axis pi of n, it's a step function that roughly looks like this. And then Gauss, eventually discovered that this looks kind of logarithmic, more or less, and he was able to conjecture what's known as the prime number theorem, one of the most celebrated theorems in number theory. 15-year-old, I thought he was 19, whatever. Carl Friedrich Gauss and Murray both discovered an approximate formula for pi of n, which is roughly n over log n, or x over log x. So here's a table. Again, pi of n up to 100 is 25. But if you do 25 divided by the log of 25, you get 21.7. No, not so bad. You're only off by 4. And let me move it a little bit here so you can see. Here's the difference between them. Pi of n minus n over log n. And you see the difference increases, but eventually the proof of the prime number theorem is that these two things are actually equal asymptotically, meaning as you go off as x or n goes off to infinity, the ratio goes to 1, meaning the higher we go in the number line, the better and more accurate this approximation becomes. So now, let's see. Okay, so hold on. So these are just simple consequences of the prime number theorem from here. Simple consequences is that the approximate probability that a number n give me any n. The approximate probability that that number is a prime number is 1 divided by its natural logarithm. You can actually approximate that piece of p of n from here, the p of n that I had from here. You could actually approximate this function using the prime number theorem, using exactly the second thing here, because the nth prime is approximately n times the log of n, and so forth. But it so happens that n over log n is, or ln of n, ln or log, same thing to me, is it's an underestimate, meaning its graph is actually below, and that's what we'll show in the next slide. Well, actually, I thought that was the next slide. It's probably the one after. Here is an improvement to the x over log x estimate. This is called the improved prime number theorem by Dirichlet, and he conjectured that this is a better approximation. It's called the Li of x. Li stands for the logarithmic integral, which is the integral from 2 to x, 2 to whatever height you want, of 1 over ln of t dt, which is of course, and then little li is its antiderivative, so that this is equal to li of x, little li of x, minus obviously little li of 2. And you'll see, just looking at these tables here, that this is, of course, that this is indeed a better approximation than just the x log x, x over log x approximation. Even though here starts off worse, as we look at the difference, by 10 to the 18, by 10 to the 18, pi of x is exactly this. This is how many primes there is less than or equal to 10 to the 18th power. If you subtract that from x over log x, you get this huge number. But if you subtract it from this logarithmic integral, look how much of an improvement it was. That's like 3 orders of magnitude at least better. And that's just by 10 to the 18. And again, eventually we getting at asymptotic formula, approximate asymptotic equality, so that we are letting x go to infinity. And so as x goes to infinity, this approximation is even better. And so that hopefully, yeah, this is the picture I wanted to show. So in the middle, again, this is sorry for the bad quality. So in the middle, you see the step function. That is pi of x. And it's just a step function. X over log x, however, is always an underestimate. It's always an underestimate. You graph it, here it is. You see that it's always under it. And then this logarithmic integral of x, Li of x, is an overestimate, but in absolute value, it's much closer to pi of x. So this is what we mean by it's a better approximation. And so yeah, so we have these two approximations, because now we're gonna go to them. So now again, I got a lot of this stuff from this book called Prime Obsession by John Derbyshire. This is a popular introduction to the Riemann hypothesis. So enter Riemann in 1959. Riemann wrote his only paper he ever wrote on number theory, called "On the Number of Primes Less Than a Given Magnitude." It's got some French name that I'm sure Miro knows. Not some French, some German name that I'm sure Miro knows, but I'm not even gonna try to butcher it. But I'm gonna try to outline basically what Riemann did in this very short paper that revolutionized number theory. So first, let's talk about Riemann's zeta function. So Riemann's zeta function, at least for s, if s is a real number, then as long as it's greater than 1, it converges by the p-test in calculus 1 or 2 or whatever. Or whatever they called it, the p-test or whatever. So this is the definition. Zeta of s is the sum of the reciprocal numbers of n to the s. 1 over n to the s. Is 1 plus 1 over 2 to the s, 1 over 3 to the s, and so forth. Now, Riemann's starting point was what Euler had shown nearly a century before him, which is exactly this equality that the zeta function, because, and this is probably my favorite proof, the zeta function has what's called an Euler product formula, or an Euler product presentation, which is this one, which you can express this infinite sum over all natural numbers as a product over only prime. And I never started the thing, so how am I doing on time? I don't know. You guys gotta let me know. I didn't start the thing, so because I wanted to give you a short little, maybe I will, a short idea of how he came up with this proof. Let me share screen, but let me share screen too. Oh, wait. So my favorite proof. There's a lot of proofs of this, of the Euler product formula, but my favorite one has to do with the prime number theorem. I mean, with the fundamental theorem of arithmetic, and that starts with this thing. Everybody knows 1 over 1 minus x. We all know this is equal to the sum from n equals 0 to infinity of x to the n, right? So this is 1 plus x squared plus x cubed plus dot dot dot. Now, and this is valid, of course, for absolute value of x less than 1. Now, for x real, right? For this is its radius of convergence. So now let x be. So take a prime number. Let p be a prime number, so that the smallest one is 2. So p is greater than 1, which means 1 over p is less than 1. So it's indeed inside the radius of convergence. And then let x equal 1 over p into this formula right here. So we get that 1 over 1 minus 1 over p, but all of this raised to the power, eventually we're going to raise it to power s. That p, unless you let s be a number, let s be a complex number with real part of s greater than 1. Then this, for x equals p to the s, still less than 1, still in the radius, in the convergence, the interval of convergence. This will have, by that formula up here, this is exactly the sum 1 over p to the s. I mean, all of it to the whole thing to the n, which, and of course, from n greater than or equal to 0. So this is 1 over p to the n x. If we multiply it in n greater than or equal to 0. And so this is just 1 over, this is 1, it's just 1 plus 1 over p to the s, when n equals 1, plus 1 over p to the 2s, plus 1 over p to the 3s, plus 1 over p to the 4s, and so forth. And so now, by the fundamental theorem of arithmetic, if we get all these guys for every prime and multiply them all, so in other words, multiply over p prime, this 1 over 1 minus 1 over p to the s, this guy up here, which I could write as p to the negative s. If you multiply this out, and each one looks like this, so the first one is 1 plus 1 over 2 to the s, 1 over 3 to the s. If you multiply this all out, so the first one, it would be 1 plus, the first prime is 2. It's 1 over 2 to the s, 1 over 2 to the 2s, plus 1 over 2 to the 3s, plus dot dot dot. And then the next one is the 3. is the next prime. 1 over 1 to the 3 to the s plus 1 over 3 to the 2s plus dot dot dot. And if you multiply this all out, obviously the first term is 1. So the first term is 1. Then the second term, the first term is 1. Plus the second term is just this guy. 1 times this. 1 over 2 to the s. The next term is exactly this guy. 1 over 3 to the s. Plus, then the next term is going to be this one here. 1 over 2 to the 2s by the fundamental theorem of arithmetic. 1 over, in other words, 1 over 2 squared to the s. So 1 over 4 to the s. And continue. 5 is prime, so he gets his own guy. He's 1 over 5 to the s. But 6, it will be when you finally multiply 1 over 2 to the s to 1 over 3 to the s, you're going to get 1 over 6 to the s. And so forth. And this, you'll get equality and convergence, at least in this range, by the fundamental theorem of arithmetic, so that this is called the Euler product formula of the Riemann zeta function. This is equal to zeta of x, which we gave it the definition from before. So I know this is a very rough sketch of the proof of the fundamental of the Euler product formula for the Riemann zeta function that uses the fundamental theorem of arithmetic. So let me get out of here. Let me stop sharing and go back to the slides here. Sorry. Let's go back to here. So that's where this formula down here comes from. It's called the Euler product formula, and for the Riemann zeta function, and for real part of s greater than 1, we have equality, and so that was the starting point for Riemann. Hide this again. So let's continue. So now, yeah, so this was a starting point, and now this is, so we already met pi of x, but we're going to talk about some of the cousins of the prime counting function pi of x. Now pi of x is what we call a non-weighted or weighted by 1 step function, how I showed you earlier. J of x is well, he calls it J of x. It's also a prime counting function, so it's a cousin of pi of x, but it's a logarithmically weighted prime and prime powered counting function. So it's going to count whenever it sees a 4. It's going to count something, but it's going to weight it not by 1 like pi of x, but it's going to weight it by the logarithm, or the reciprocal of the logarithm of that prime to the power. So 4 would be weighted by 1 over log of 2 squared in this case. And 27 will also be counted, but with a weight of 1 over log of 3 cubed, because it's 3 to the third power. And so J of x is a prime counting function, just weighted a little bit differently than pi of x. But yeah, it's so instead of increasing by 1 every time it hits a new prime, this J of x increases by the log of the prime p, or when the number n is p to the k, it's weighted by log of p of 1 over k divided by k. So yeah, so this is j of x. You could call it a cousin of the pi of x. And they are related by this, by something called, that I don't have too much time to talk about because of time restraints, called Mobius inversion. Meaning, if I have pi of x, I can write j of x, this j of x as pi of x plus 1/2 pi of the square root of x plus 1/3 pi of the cube root of x plus 1/4 and so forth. And likewise, we can invert the other way and get pi of x in terms of j of x. So pi of x is just j of x minus 1/2 j of the square root of x minus 1/3 cube root of x, j of cube root of x, and so forth. The whole point is these two are connected by what I wrote here, by what's called Mobius inversion in number theory. And so why are we going to deal with j of x for the moment and not deal with pi of x? It has to do with some certain convergence things, and again, for Riemann's goal. So just what I said more succinctly again, pi of x can be written this way. So that this is the this is the Mobius function right here. And pi of x is exactly this sum over, you can write it as a sum over j of x. But with coefficients, the Mobius numbers, the Mobius function. So now, this is what the graph of x, like I said, it's still going to be a step function, but now you'll see in a moment why we're going to use it instead of pi of x. So here's j of x graphed on the y-axis and x on the x-axis. Again, it still looks like a step function, and if we wanted to take the integral j of x, for example, from 0 to infinity, of course, just like pi of x, it's going to have infinite area under the curve, under the step curve. If we took instead of doing a Riemann sums as vertical things, you could take them horizontally as well. And so for j of x, the horizontal strips look like this. But they would look similar for pi of x, only you'd have pi of x on this axis. But here, this is the question now. These horizontal strips in this Riemann sum of j of x, we're going to multiply them by a factor of x, necessarily by a factor of x that's going to make the integral converge. And that factor is going to be exactly this one. So the answer here lies in multiplying j of x by a factor, say x to the negative s plus 1, which is x to the negative s minus 1, to force it to decrease faster and converge. And what it does to that picture from before, it's going to start making it that a step function is going to start looking like this. And so we're going to, instead of considering j of x only, we can consider j of x times x to the negative s minus 1. And let's say here's a randomly chosen s, because all we care about is that the real part is greater than 1. At least for now, because we haven't talked. I don't think I'll get to the functional equation, even because yeah, this was a 2-part lecture the first time. But the whole point is, this now has a chance. This integral, the integral of j of x times x to the negative s minus 1, now has a chance of converging, and in fact, it does converge. And the area under the curve, so we're talking about this integral here. And again, here, this is a randomly chosen s. We're talking about this area under the curve. And this actually converges. And since it converges, we can now unleash the entire power of calculus and complex analysis. And we're going to try to find the formula for this And again, once we get a formula for this, so yeah, once we get a formula for this, we'll be able to go back and get a formula for pi of x, which was our original motivation. So yeah. Oh yeah, why are we using this, you might ask? Well, it has to do with, if you remember that I kind of showed you the derivation of the product, the Euler product formula for the zeta function. Well, when you have something written as a big long product, what happens when you take the log of a product? Everybody should know this. Well, the log of a product, so if we just wrote the sum function, the sum definition here, not very useful. But you write that log, the product formula, so here, I wish I could write. Oh, I could. So here, I have log 1 over s, who cares? Log, but not of the sum 1 over n to the s, but of the product over the prime of, again, 1 over 1 minus p to the negative s. The log of this product is going to expand. And Riemann was able to show is they term by term it expands, and once you evaluate each term, he got this almost what I call almost magical formula, that the logarithm of zeta divided by s is exactly the integral, this here, the area under the curve, the integral from 0 to infinity of j of x times x to the s minus 1. So this is from this magic formula is where Riemann got his inspiration to look for the analytic expression for pi of x. Because if we can go from this, so this is the idea. So Riemann's goal was to again find an analytic expression for pi of x. So the idea is we saw how to express pi of x in terms of j of x. We saw that earlier. And using Mobius inversion and this magical formula, we're going to use it to express j of x in terms of the zeta function. So the idea, put them together, this is a simple syllogism. We can express pi of x in terms of something that has to do with the zeta function. That's the short and cute version of it. So now, yeah, this is pretty much over. The thing's over because, like I said, this is a 2-part presentation. I can't get to the second part. But now Riemann's goal was achieved because he achieved this here. And what he achieved was this. He was able to write, after doing everything, using complex analysis and all that, he was able to write j of x, the function that's related to pi of x. You could write pi of x in terms of j of x. He got an analytically closed formula for j of x, namely, it's the logarithmic integral of x, the one that we saw earlier, minus this sum, minus log of 2, which that's just a constant, minus this integral here, which, again, this is not too bad. This is a convergent. The last term is not a problem. This is just a constant. This is just the logarithmic integral, again, not a problem. So it's this second term here where all the interesting stuff happens. And this is where the connection to prime numbers are. Because remember, see, this this sum here is over rho, where rho is here is a Greek letter for r, standing for roots. And this sum is over the roots, the zeros, or the roots of the zeta function. That is the complex numbers rho such that zeta of rho equals 0. And so that this is where the zeros, the famous zeta zeros, come into the picture, because the analytic formula for pi j of x and therefore pi of x depends on the zeros of the zeta function. And namely, the more order the zeros of the zeta function have, for example, the Riemann hypothesis is that they all have real part 1/2. They all lie on this, what famously called the critical line. The more order the zeros of zeta have, the more we can control this term. We can control this second term. And then the more regularity the formula for pi of x will exhibit. That's the idea. So like I said, I'm not getting too rigorous into this. I'm more just giving you guys the ideas. But this is the main idea, and this is where the zeros of zeta come into the picture. They come in here. This is the only term of any difficulty or even interest, really, because Li of x, remember, was already a good enough approximation. The error term is completely controlled by the zeros of the zeta. And the regularity of the zeros of the zeta function will determine how complicated or how regular or how irregular the prime counting function is, meaning the distribution of prime numbers. And guys, that's it. I believe that's it. I'll take any questions, of course, but so yeah, this was the main point. The main point is this term right here. Again, is the error term is the main part of the error term of the logarithmic integral, and it controls the regularity of the distribution of primes. All right. So thank you all for your attention. Now I guess I'll take any questions if you have any. If not,
Thank you for your that was a very
Yeah, I
interesting
have
presentation.
hold on. Let me
yeah,
stop sharing this.
I have a question. Hello?
Yeah,
Okay.
hold on. Let me stop sharing the screen.
I mean, it's just I want to know how is
Hey,
the
what's up,
x
Jose?
over ln x? Hello, Camilo.
Hola, Gail was here. Nice to see you. What was your question?
That just I don't know how I mean I don't understand how x over ln x is approximating the I mean I know it's a very famous theorem, but I don't know exactly how. Do you know or?
Well, I mean, no. Originally, I guess, I mean, I know I would say a good deal of the history of this. I know Gauss was, I think, the first to I mean, some people claimed it after, like Legendre or whatever. But Gauss was like, man, this has been in my notebooks since I was 18. And I believe it was a heuristic result. I believe he just started compiling charts like I showed you, and saw how similar, how good of an approximation it was. Because again, they are already focusing on just pi of x. Because p of x, the one, or p of n, the one that gives you exactly the nth prime, that function is probably too much to ask for. Too good. So the next best thing was the prime counting function. And I think Gauss just heuristically, he just noticed the pattern. Because he was Gauss. All hail, in Gauss we trust. I believe he just noticed the pattern and made the conjecture. And he calculated, I guess, as high as he could, and saw it was a decent approximation. I mean, and then it was a rush for good 50 years until they actually proved the prime number theorem. Eventually, by the late 1890s, two different guys independently proved it. They had to use complex analysis and stuff that Gauss wasn't even thinking about probably at the time when he first came up with it, because like I said, he's probably like 18. But yeah. But where did it come from? I don't know. Gauss famously liked to always hide all his dirty work and only show the final result like on a pedestal. And like he believed the details were unnecessary and he just showed the final. So we don't really know how. It's pretty hard to tell how he even found that formula.
That's
However, clearly it led to a lot of progress in number theory. And then Riemann took it and ran with it.
Someone else is gonna think like this. Wow. Really? That's
I'm
interesting.
sorry, I can't hear you. I apologize.
I'm mumbling to myself.
Oh. Sorry. Okay, well, I guess anybody else have any other questions? Like I said, this does have a second part where I do prove that I prove not not a sufficient condition, but a necessary condition for the Riemann hypothesis called Hardy's theorem, which the necessary condition is that at least infinitely many of the zeros of the zeta function. I mean, because if you can prove that only even just one zero is off the 1/2 line, then you have successfully disproven the Riemann hypothesis. But of course, they've shown it. They're up to like the trillions and trillions and trillions of the first zeros of the zeta function have all lie on the critical line, the 1/2 line in the complex plane. And wait, hold on, there's a chat. Let me open it. It's just people saying thank you. So yeah, like I said, there's a second part to this presentation. However, yeah, today obviously I don't have time. It's already 4:55. So actually, right on time, pretty much.
Thank
So
you.
yeah, everybody else, thank you for attending.
Yeah, thank you. Thank you.
Like I said, I wanted to give this talk because I feel like I probably kept most people's interest. You know, like had pretty pictures and talking about something not too abstract. Whereas if I would have started talking about, representation theory and representation of Lie groups and stuff, chances are I would have ended up talking to Gail and Miro. Like this talk would have not been, and all of you guys would have tuned out a long time ago.
Well, thank you.
And
for
eventually I realized what's the
tuning
point of it. If I'm gonna do these talks, I mean, I'll do those other talks for just them. We'll go into the details and stuff. But if I do one of my research talks, at the moment, my research talk would be kind of pointless for an audience like this because most of you are just gonna tune out within the first 10 minutes, probably. Because the second I start talking about the geodesic flows of symmetric spaces, unless you're familiar with differential geometry and stuff like that, and some representation theory, because that's where I'm going. That's where I would be going quickly. People would tune out pretty quickly. So I didn't want to do a talk just for Gail or just for Yota. So I wanted to do a talk that was more accessible to everybody and keep everybody's interest.
Now, so
Yeah, I want to thank everybody for coming.
Yeah.
Everybody else, oh man, Professor Yotov's writing in Bulgarian is not fair. Write in English. For all I know, actually I could copy it and translate it.
It's not for you, it's for your advisor.
I know, but guess what? I'm gonna copy it and translate it. Do you know they have Google Translate, my friend? For all I know, that says your student's an idiot, and so I'll find out very soon.
Okay.
This is over. I'm translating that. So you might as well tell me what it says. I'm translating.
Find out yourself. It's a good homework.
It's not even a homework. It's gonna take me
Yes,
2
of
seconds.
course.
Copy and
If
paste
you,
into Google.
especially if you post it for yourself.
How is that homework? I'm gonna copy and paste it into Google. That's it.
Look,
And I'm gonna
won't.
translate.
Camilo, if you have an advisor who is a Bulgarian, you have to learn a bit of Bulgarian. Don't.
Oh no, I wish, man.
It's part of the qualifying exams, you know.
Yeah.
No, yeah. And I know about how a lot of doctoral programs do have this language requirement. God, I'm lucky, because I don't know, man. I might be a little too old to like really. No, math-wise, I probably could learn German or French, but to fluently learn another language, actually, that is not like Italian or Portuguese or pretty similar to Spanish. I'm kind of screwed. It would be pretty hard for me. I'm not gonna lie. I don't think I can learn a language very easily at this point.
Okay.
But everybody,
Camilo, I
again,
have to go.
yeah, I gotta go too.
Very nice.
Thank you, everybody.
Thank you.
Especially Miro, thank you for coming. Thank you for coming, Svetlana. Thank you for coming, Gail, because Miro's seen this talk before. He even saw part 2 of it. Gail, I don't even think Gail knew me. I was still a lonely undergrad. So,
Bye.
all right, everybody, have a good one.
Thank you for coming.
See you guys next week. Let me see. Yeah, I gotta stop recording.